Hello everyone and welcome to today's lecture. So today we're going to be covering a very interesting topic which is super applicable to computer science, and this is the idea of what's called orders of growth of functions. And right off the bat there are two separate notations that are very important to understand um, in terms of describing the growth of functions and comparing the growth of functions. Um, the different notations can sometimes get confusing, but both of them have benefits and advantages, and both of them also have disadvantages. So when I teach this, I like to present both different notations so that you can understand the big picture in terms of how we describe function growth. This topic is super important for understanding growth of algorithms and just generally measuring complexity in computer science and in mathematics as well. The main idea that we want to understand is exactly what it means when one function f, say, dominates a function g. Or vice versa. And I suppose I'll actually switch these two. Because typically we use f to denote the more complicated function, and g is a simpler function. So big O notation has been widely used in mathematics for more than a century. It was first introduced by Paul Bachmann in 1892 in a book on number theory. The big O symbol, sometimes called the Landau symbol, is named after the German mathematician Edmund Landau, who used the notation throughout his work. And it was really popularized in computer science by Donald-Knuth, who also introduced what's called the big omega and big theta notations that we'll define throughout the course of this lecture. But the other notation that I think is very useful and important that we're going to talk about is what's called Hardy's notation, which I think makes some of these concepts a little bit easier to understand because it sort of rephrases the definitions of big O, big theta, and big omega into a symbol that's, in some sense, it's very similar to the strictly less than symbol, or the less than or equal to symbol. But we'll see that the propositions that we need to define these concepts are really the same propositions. So I'm going to start by defining the notation, and then we'll move into defining exactly what mathematically the notation means. So in the following, we're going to take either functions from the real numbers to the real numbers. So f, g, and l are going to be either functions from the real numbers to the real numbers, or f, g, and l are going to be functions from the natural numbers to the real numbers. And I'm going to make a table here of the meaning. The Hardy notation and the Landau-Knuth big O notation. And the book doesn't mention the Hardy notation at all, but it focuses on just the Landau-Knuth big O notation. However, I think both the Hardy notation and the Landau notation are very, very important to understand, which is why we're going to go through and discuss this. So the meaning here is going to be that we'll say that the function f is dominated above by a function g in the Hardy notation. You write this as f, and then something that looks similar to a less than or equal sign, but is actually curly, g. And I really want to emphasize that. This is not less than or equal to. This means function f is dominated by g. In big O notation, this is written as f is big O of g. Correspondingly, we have the notation that f, the meaning that f is dominated below by some function h, say, in the Hardy Littlewood notation. This is a very nice expression. H is dominating f below, and very shortly we'll show that in Landau-Knuth big O notation, this is the same statement saying that f is big omega of h. And the next concept that we will define later on in the lecture is f has the same order of growth of g. By the way, this is equivalent to saying that f is, instead of g, to make things a little bit more clear, I'm using a different function, I'll say L. This is the same thing as saying that f is bounded both above and below by the function L. In the Hardy notation, this is noted as f line squiggle L, and it's the same thing as saying that f is bounded below or above by L, and f is bounded below by L. And not surprisingly, in Landau-Knuth notation, this is the same statement as saying that f is big O of L and f is big omega of L. which has a much simpler statement, we introduce a new symbol for this statement that f is big O of L and f is big omega of L to just be f is big theta of L. So without seeing some specific examples, it might not be clear exactly what we mean by these symbols. We have to first define exactly what we mean, but I wanted to make this table right here for the various notations so that you don't get confused throughout the course of the lecture. I do have one more thing that I want to add to this table, and this is the statement that f is strictly dominated above by G This has a rather nice notation or nice expression in the Hardy notation. We can go through and say that this is in the Hardy notation given by the expression f curly less than sign G. This is the same thing as saying that f is dominated above by G and the negation of the statement G is dominated by F. Or in the Landau notation, this is F is big O of G and F is not big theta of G. So these notations are, we'll see, are very, very useful and have a very sort of intuitive definition using ordering on the real numbers. Because we know that these functions are going into the real numbers in either case. And let's go through and define exactly what we mean. So let f and g be functions from before. So either from the real numbers into the real numbers, or the integer, or the natural numbers into the real numbers. We say that f of x is big O of g of x. Remember, this also means in the Hardy notation that f curly less than or equal sign g if there exists constants c and constants k such that for all x, if x is greater than k, then the absolute value of f of x is less than or equal to the constant c times the absolute value of g of x. And this is essentially stating that eventually, right? We can find a constant c and a constant k, such that if x is greater than this constant k, the function f of x will always stay below some constant c times g of x. And this is what we mean by f is dominated by g. This is a very important relation on this set of functions that we've considered, and it's important for many reasons, but it's very, very important in dealing with and understanding the time complexity of algorithms, or just the complexity of a certain procedure, a counting procedure maybe. And we're going to see as we develop this lecture and these ideas, right, how important this really is in computer science and in mathematics as well. So a big theorem that we have is that the dominance relation is a reflexive and transitive relation on the sets of functions considered, which is the sets of functions from natural numbers to the real numbers, and the sets of functions from the real numbers to the real numbers, and even sets of functions from the integers to the real numbers. So the proof of this theorem is relatively straightforward. By now we know very well the properties of reflexivity, transitivity, and symmetry. We only have transitive and reflexive for the dominance relation, but the idea is that we have that right, you can actually pick any k to show reflexivity in the domain of definition of the function. And then by definition, right, for all x greater than k, the absolute value of f of x will always be less than or equal to the absolute value of f of x. So we've chosen c equals 1 and any value of k in the domain of definition for our witnesses to this inequality. And this will always be true, because the absolute value of f of x will always be equal to the absolute value of f of x. Therefore, f is dominated by itself, or f is big O of itself. For the transitivity property, we have to be a little bit more specific and do a little bit more work. We assume that if f is dominated by g, then there exists some k1 and c1 such that for all x, if x is greater than k1, then the absolute value of f of x is less than or equal to c1 times the absolute value of g of x. And we also assume and really it should be assumed that f of x is dominated by g of x, and that g is dominated by some h, in which case there exist constants k2 and c2 such that for all x, if x is greater than k2, then g of x in absolute value is less than or equal to C2 times h of x in absolute value. And using these two assumptions, we see that if we set k equal to the maximum value of k1 and k2, then for all x greater than this k, both of these inequalities will hold, which means that the absolute value of f of x will be less than or equal to c1 times c2 times the absolute value of h of x, which is equal to c1 times c2 times the absolute value of h of x, which gives us a constant c that satisfies the definition of domination for f of x with h of x. So then we've just shown that if f is dominated by g and g is dominated by h, then f is dominated by h, which shows transitivity. So therefore, we conclude that we've shown both reflexivity and transitivity for this dominance relation, which is a really kind of cool and neat thing to see, that we can have relations on sets of functions. And this is going to be super important when we get to what's called the same order relation, because it turns out that the same order relation is actually an equivalence relation, which means it partitions the set of functions that we're talking about into equivalence classes that are equivalent in the order of growth of the functions, which is a super important idea because we want to be able to prove certain statements about the growth of algorithms, and in order to do that, having this partitioning is extremely important. So I want to note here that the strict domination relationship which we defined above as f is strictly dominated by g if f is dominated by g and g is not dominated by f, is also reflexive and transitive. And this is a relatively straightforward extension of the proof that I just did. But what we want to do now is move on to rigorously defining the next thing in the table, which is the big omega notation, or the concept of being dominated below. And we're going to see that this has a very similar definition to being dominated above, and is actually in the Hardy notation denoted in the exact same way as the domination relation, which is very cool. So take functions f and g, our functions as above, defined at the beginning of the lecture. We say that f is big omega of some L if there exist constants K and C such that for all x if x is greater than k, then the absolute value of f of x is greater than or equal to c times the absolute value of L of x. And this is equivalent to saying that f is bounded below by L. For instance, I want to make a specific note here. If f is big omega of L, then we have that there exists a k and there exists a c, such that for all x greater than k, we have that absolute value of x, f of x is greater than or equal to c times the absolute value of L of x. This is mathematically the exact same statement as absolute value of L of x being less than or equal to 1 over c times the absolute value of f of x, which is the same as saying that L of x is dominated, or L as a function is dominated above by f. So the big omega notation is equivalent to the Hardy notation, which is super helpful and motivates the notation table that I talked about before. Now, I want to point out here that c has to be a positive constant in the case of the big omega notation, because we're talking about a lower bound on the function f. In our previous definition for big O notation, we didn't have to specify this because we were talking about an upper bound on the absolute value of f, which would essentially mean that in the previous definition, c has to be positive by definition. But because it's a lower bound, we really have to be careful and specify that c is a positive constant here. So the last thing that we really want to go over and kind of define is the idea of when two functions have the same order of growth, and then we can go through and see some examples and theorems that relate all of these properties. So for functions f and g as before, if f and g are both dominated by one another, in other words, f is dominated by g and g is dominated by f, then we say that f and g have the same order of growth. Denoted by f line tilde g or in the big O terminology, we say that f is big theta of g. And what's really neat here is that the order of growth relationship is an equivalence relation on the function space considered. So either on the set of functions from the natural numbers to R, the real numbers, or the set of functions from the real numbers to the real numbers. Showing this is relatively straightforward, just like before. We showed reflexivity for the order for the domination relationship. Really, reflexivity for this order of growth relationship is a relatively straightforward extension of that. So I'm not going to go through it here. This is a simple extension of the previous proof. Same thing for transitivity. But for symmetry, we might want to show, go through and actually prove this. Remember that the domination relation and the strict domination relation are not symmetric. However, it's relatively simple to go through and show that if f is has the same order of growth as g, this is the same thing as saying that f is dominated by g and g is dominated by f, which we know that these are two propositions, therefore we can reverse the order of the and now relatively simply we've obtained that g has the same order of growth as f. So this is a symmetric relation. And what's really neat here is that what this is essentially saying is that if we form the quotient set for either the set of all functions from the natural numbers to the real numbers, mod this equivalence relation, this is the set of equivalence classes of functions with the same order of growth. Same thing if you consider, say, the set of functions from R to R, mod this equivalence relation. And what this is saying then is that if you can show that two functions are have the same order of growth, then they're essentially equivalent to one another under this equivalence relation. So they lie in the same equivalence class, which means if we're analyzing algorithms, showing that a given algorithm has a certain order of growth is enough, right, to say that it's equivalent to any other algorithm in this class, and it grows at the same rate as any other algorithm in this class. So this is, an extremely important idea in complexity theory and complexity of, the growth of algorithms in computer science. But so what we'll do right now is go over a number of different examples, and without proof, I'm going to write down the following relationship that's really important to remember, and I will prove some of these, but not all of them. All of them are proven in the book, and we'll go over some very specific examples of these a little bit later on in the lecture. But one is strictly dominated by the function log n, which is strictly dominated by the function square root of n, which is strictly dominated by the function n, which is strictly dominated by the function n times log n, which is strictly dominated by the function n squared, which is strictly dominated by n cubed, which is strictly dominated by the function 2 to the n, strictly dominated by the function 3 to the n, which is strictly dominated by n factorial, which is strictly dominated by n to the n. And there are many other equivalence classes in between these functions, but these are a lot of the common strict dominations that you'll see. And so what I'm going to do is start by just kind of looking at visualization of all of these dominations, right? These strict dominations, and really try to emphasize why these are true. So if we take a look here at this plot, see a number of different functions on this plot, but we'll start with the first three: 1, log n, and square root of n. This black dotted curve right here is log n. This straight solid line is the function 1, constant function 1, and this red dashed line is the function square root of n. And you see very clearly that eventually, right, once we passed k equals 10, the log n function is staying above the constant function 1, which is directly staying below the constant function square root of n. It's bounded above by square root of n, and this is the case regardless of how far out you choose to go for these functions. So if we change our scaling a little bit, we stretch the axis down, and I'm going to get rid of the labels on the lower two functions. I'll just leave square root of n there to see what's happening as we change our scaling a little bit. This blue dotted line right here now is representing the constant function n, or the linear function n, and this orange dashed line is the function n times log n. You see, just like before, n is strictly dominating the function square root of n, which is being strictly dominated by the function n times log n. Continuing this process, by stretching down our scale along the y-axis, we see that the function n times log n is eventually strictly bounded by the function n squared, which is eventually strictly bounded by the function n cubed, which is eventually, past n equals 10 here, strictly bounded above by the function 2 to the n. And no matter how far out we go, this still holds. So again, we're going to remove some of these earlier labels as we go up in scaling, so as to not get too confusing with all of the labels. And furthermore, then we now see that the function 3 to the n right here is dominating the function 2 to the n, and 3 to the n is subsequently being dominated by 4 to the n. And all of these power functions, these exponential functions, are in turn being strictly dominated by the function n factorial, which is this blue function right here. And the n factorial function itself is being strictly dominated by this orange dotted function right here, which is the function n to the n. So this is a sort of graphical proof, right, of each one of those strict domination relations that I've just shown. And now we want to go through and kind of prove some of these. I'm not going to go through and prove all of them because that would just take way too much time, but I do recommend you go through and search out in the book and search for the proofs of these so you can understand, right, how to kind of construct proofs for showing different orders of growth. So let's go through and try and show some of these strict domination relationships. We're going to start with the very end for the largest functions here, in some sense n factorial and n raised to the power n, because in some sense these are relatively straightforward to go through and definitively show. And I want to make a note here that we defined strict domination of a function f by a function g to be f dominates g and the negation of g dominates f. So remember that f dominates g is the expression for the mathematical statement that there exists a k and a c such that for all x greater than k, absolute value f of x is less than or equal to c times absolute value of g of x, which means that the negation of g dominates f is the expression that for all constants k and for all constants c, there exists a number x, or a value x, so that x is greater than k and absolute value of g of x is strictly greater than c times f of x, absolute value. And we can see this relatively straightforward manner if we look at, well, this is the definition of f is dominated by g, which means that, equivalently, or a logically equivalent statement to this is there exists a k and a c such that for all x, x is less than or equal to k, which is the negation of this statement, or this statement, which is that absolute value f of x is less than or equal to c times absolute value of g of x. And this is where our skill in manipulating predicated statements is very important, because this then means as well that G is dominated by F is the same statement as there exists a K and a C such that for all X, if X is greater than K, then G of X is less than or equal to C times absolute value of F of X, which is the same statement as X is less than or equal to K, or G of X in absolute value is less than or equal to C times F of X. So the negation of this statement is the negation of this quantified statement right here, which is the same thing as saying for all constants K and C there exists an X such that X is greater than K and G of X is strictly greater than C times F of X. So this is the logical statement that we want to think of when we go through and try to prove a strict domination. So we'll start with the first part of what I said, which is to go through and show the following: that n factorial is strictly dominated by the function n to the n. And remember, the factorial function is defined by 0 factorial is equal to 1, and for all n greater than or equal to 1, n factorial is n times n factorial. So with this definition, we have a relatively straightforward method for going through and getting this estimate. To show that it's strictly dominated, we first need to show that n factorial is dominated by n to the power n, and we know that n factorial is 1 times 2 times 3 times all the way up to n minus 1 times n, and we know that 1 is strictly less than n for any positive n greater than 1, 2 is strictly less than n, 3 is strictly less than n, and so on and so forth. N minus 1 is strictly less than n, and n is less than or equal to n. And this is just equal to n to the power n. Therefore, we have a big O estimate here, taking C equals 1 and K equals 1 as witnesses, because when n is strictly greater than K, or strictly greater than 1, right, this strict inequality will always hold, and therefore n factorial is dominated by n to the power n, or n factorial is big O of n to the power n. Now, this is a little bit informal, but the idea here is that this idea is really kind of a proof sketch. This idea can be directly written up using mathematical induction. So induction on n here. And that would be a good practice problem for you to go through and look at. But for part 2 of the proof, I'm not going to go over explicitly how to do it, but you can do it relatively easily by contradiction and by using the fact that n factorial has to be strictly greater than n to the n. So it might be a good exercise to go through and do that. Now that we've proved this theorem, we actually have an interesting corollary from this theorem, and that's that we actually get almost a free domination estimate. And this is the following. It's that the function log of n factorial is big O of n times log of n. Or in our Hardy notation, that log of n factorial is dominated by n times log of n. Right? And the reason that this is almost, it's a very immediate corollary is that, well, we've shown up here that n factorial is strictly less than n to the n for n greater than 1, and therefore log of n factorial is going to be less than log of n to the n, which is n times log of n. So this is very neat, and it's showing something very, very useful for future investigations. Now I want to give an example right now that is a very kind of fun toy example. A lot of students and people in general have a hard time conceptualizing how fast the factorial function is actually growing, and it's really, really, really fast. At the end of the lecture, we'll see definitive definition for how fast this is, but the idea is that I want to give you kind of a fun toy example to think about. And the idea here is, suppose that you have a contract with Elon Musk such that he will pay you n factorial dollars if his account balance goes into the red. It means he doesn't have enough money to cover his account balance. And just for the sake of assumption, right, let's use his current net worth as the amount of money he has in his account. So his current net worth is 176 billion. And that's 176 with 9 zeros after it. And we'll look at the first couple days. First day, 1 factorial. The second day, 2 factorials, that's $2. Third day is 3 factorial, so it's 2 times 3, which is 6. The fourth day is 4 factorial, which is 4 times 6, or 24. So initially it doesn't seem like this is going to do much to his net worth, but sure enough, if you get up to 14 factorial, this is 87 billion 178 million 291,200. So after 14 days, we've amassed that much money. And on the 15th day, 15 factorial is 1,307,674,368,000. And this 15th day is when he has to pay up, and he actually goes into the red by a lot. Right? He goes into the red by 15 factorial minus his net worth, which is 176 billion. Or he's going to owe you 1,131,674,368,000. Oops, and I just realized I shorted myself. One more zero here and one more zero here. So I think this is a very cool example showing how fast the factorial function grows. Right? After 15 days, you're all the way up to over 1 trillion.